All right. So in this segment, we're going to talk a little bit about the normal distribution. Okay. So so as economists started to collect more and more social data, okay, and they started, to draw histograms for the data that they were collecting, what they saw was, if you look at a bunch of histograms of real data, it isn't totally, it's like one histogram looks like one thing, then another histogram looks totally different. You look at these histograms and you start to realize that the same patterns start to appear in a lot of these histograms. Okay. And uh, three of the most common types of histograms that you'll encounter are the normal distribution, the log normal distribution, and the Pareto distribution. Okay? And of these, perhaps the most famous is the normal distribution. You look at a lot of different data sets, and you'll find that a lot of the data in those data sets are normally distributed. Okay? So, okay, I'll give you 4 examples of normally distributed histograms. Okay? Number 1, this is the sum of 6 consecutive, the sum of a dice, a 6-sided dice, rolled 10 times. Okay? So you take a dice, you roll it 10 times, you add up those numbers, you write it down. You do it again, you write it down. You do it 1,000 times, and you look at the relative frequencies of those sums, and you find that that obeys a normal distribution. Okay? So this is a normal distribution. Okay, let's look at a second example. Okay, we're going to look at a Galton board. Okay, and I'm just going to play a little bit of this video for you.
Today we're going to talk about the Galton board. Invented, or at least named after Francis Galton, what we have is a bunch of pegs and a bunch of slots. Now when I turn this over, all of these balls, 3,000 of them, will fall through those pegs and they'll scatter randomly, in the sense that we don't know where each individual ball will go. But because there are so many of them, out of chaos comes order. Look at all that wonderful, wild randomness turning into pretty much the same exact shape every single time. A normal distribution. Let's begin by
Okay, so there's a Galton board. Okay, this guy actually, I knew this guy in college. Okay, okay, let's look at a third example. Okay, so SAT scores, as it turns out, are distributed normally. Okay, so you can see here are some SAT scores from the year 2010. We plot them. Hey, looks like a normal distribution. Okay, and finally, the height of people is distributed randomly. So if we consider, for example, the heights of people in our class, that follows a normal distribution. And in fact, you can see here's some data for the heights of men and women, and we see that they actually each follow their own normal distribution. We have a normal distribution for women, and then we have a separate and slightly higher normal distribution for men. Okay, so now here's my question for you. Why are all 4 of these things distributed normally? Okay, I mean, because think about it, right? We got the heights of men and women. Okay, we got SAT scores. We got balls rolling down this Galton board, and then we got the sum of a bunch of dice rolls. I mean, how do any of these things have anything in common? Right? I mean, isn't it sort of mysterious that all 4 of these seemingly unrelated processes generate the exact same histogram? Well, it is quite mysterious, okay? The reason for it is that actually there is something linking all 4 of these phenomena, okay? You see, normal distributions tend to arise when many independent factors are added together. Normal distributions arise when many independent factors are added together. Okay? So, for example, okay, over here I have how I got that first normal distributed plot here. Okay, so this is actually some data that I generated. What I did was I had the computer roll a bunch of dice for me. You see, the computer here has rolled a six-sided dice 10 times. Okay, so here's my first trial. You know, um, 10 rolls of a six-sided dice. We got 6, 5, 1, 4, 1, 1, etc., etc. Okay, I took those numbers and I added them up, and I got this sum, 36. And then I just proceeded to do that 1,000 times. Okay, and if you look at the distribution of this sum here, okay, you can see that it is normally distributed. Now, what is this sum? This is as the name suggests, the sum of a bunch of completely random, independent rolls of a six-sided dice. This, fundamentally, is what generates a normal distribution. Summing a bunch of random factors generates a normal distribution. So all of these other instances of a normal distribution somehow are equivalent to that. Okay. Okay, let me show you how they're equivalent. Okay, so first of all, the Galton board. Okay, so, okay, let's think about what's happening here with the Galton board. With the Galton board, we have a number of different, we have a bunch of these metal balls that are in this top area, right? And all of a sudden we flip the board over and they're allowed to fall down. And you can see what happens is they enter into this grid of pegs. And what these pegs do is that when the ball hits one of these pegs, it has a decision to make, right? It either moves left or it moves right. It has to go in one of those two directions. And then at the next row, it'll encounter another peg, and then it has to move either left or right. Okay, so basically, to determine this distribution down here, to determine where the ball ends up falling, is just a matter of how many times did the ball move left when it hit a peg versus how many times did the ball move right when it hit a peg. If you wound up all the way on the left side of the Dalton board, that simply means that ball happened to move left many times in a row. Okay, so imagine that moving left is represented by -1 and moving right is indicated by a +1. Well, then the final sum, okay, of those plus and minus ones represents the position that a given ball will be on a Dalton board. Okay? And remember that each one of those minus ones or plus ones moving either left or right is essentially random. Okay? So this Dalton board can be boiled down essentially to adding up a bunch of random left or right choices. Now, what did I say before? Normal distributions arise when many independent factors are added together. Well, that's exactly what this is. Okay. Now you go, what about the SAT example? Well, same thing. So your SAT score is simply the sum of your score on each question on the test, right? Now, of course, they scale it up. They scale it up, so it's a larger number. But basically, your SAT score is just how many of those questions on the exam did you actually get right? It's the sum of your score on each individual question. Okay? And since you have a certain probability of answering each question correctly, this situation, again, is kind of like adding together a bunch of random dice rolls. Those dice rolls, in this case, representing the likelihood that you get a particular question on the SAT right. Okay? Finally, what about height? You go, there's no way height is the sum of a bunch of random choices. Is there? Well, the answer is actually yes. So as you guys know, that so height is primarily genetic. Okay, so it's not entirely genetic. Okay, what nutrition you receive as a child also influences it, but much of height is basically genetics. Okay, and of the 20,000 genes in your DNA, roughly 700 are known to contribute to your height. Okay. Now, here's the thing. For each copy of those genes, you inherit one version from your mother and one version from your father. That's sort of how genetics works. Okay, for each gene, you have two copies of it, one from your mother and one from your father. And they, in turn, each inherited their height genes from either their mother or their father, your paternal and maternal grandparents. So in this way, your height is determined in a way not so different from answering a bunch of questions on the SAT, right? So what I mean to say is, okay, here I have, let's say that these are your four grandparents, okay? You see, for any given gene that you have, you could have inherited it four different ways. You could have inherited both copies of the gene from your paternal and your maternal uh, uh, male grandparents. Okay, that is to say you could have gotten the gene from your mom's mom and your dad's mom, or from your mom's, from your mom's dad and your dad's dad, okay, or from your mom's mom and your dad's dad, or from your mom's dad and your dad's mom, or from your dad's mom and your mom's mom. Okay, hopefully that makes sense. There's four different types of combinations of your four grandparents. Okay, and so, okay, so these four patterns of four ways that you could inherit a particular gene, that determines basically the contribution of that particular gene to your height. Okay, and so when when nature sort of determines what your height is, it's kind of like nature sits down and answers 700 SAT questions. And for each of those SAT questions, it chooses how your gene for that particular gene is going to be inherited, whether it's going to be inherited from one combination of your grandparents or another. Okay, and so in this case, height is a lot like kind of the SATs. And the SATs are an example of the sum of a bunch of random choices. And so once again, here with height, we have a normal distribution. Okay, hopefully that makes sense. Okay, so that explains why many things we observe in nature are actually found to be distributed normally. Okay, in the next section, we'll talk about a couple of other commonly seen distributions. The normal distribution, like I said, is the most well-known distribution, okay, but there are actually quite a few others.